event we have today. This webinar is being recorded and will be posted on the CUAHSI YouTube channel soon. Secondly, we ask that you use the Q&A functionality to submit questions to our speaker today. And please feel free to do that throughout the talk. We'll have time for some discussion at the end. And finally, we expect that all involved with CUAHSI cyber seminars promote and maintain a professional, considerate, and respectful virtual environment. So thank you for being a part of that. Thank you again for joining us, and to Kristin and Raub for putting together a fantastic lineup of presentations, and to our presenter today for joining us. Today's session is How Effective is Green Infrastructure for Stormwater Management, presented by Dr. Moira Zellner. And with that, I will pass the mic to Kristin and Raub to introduce our speaker.
Thank you, Julia. I just want to echo what Julia said. Thank you very much, Moira Zellner, for joining us today. I'm very excited for your talk. So today we have Dr. Moira Zellner, who is a professor of public policy and urban affairs and the director of participatory modeling and data science at Northeastern University. And without further ado, I will turn it over to our speaker and join you again at the end to help facilitate some questions. Thank you.
Thank you very much, Chris. I'm going to go ahead and share screen. Here it goes. So you should all be seeing. Is it coming through?
I see a black screen.
Let me stop. Let me share again. Okay, can you see that?
Yes, now I can see it.
Okay, good. That's a relief. Okay, hello everybody. Thank you, Kristin and Julia and everybody at CUAHSI for having me. I'm always excited to be part of these conversations. And so what I'm going to present today is a little bit of my trajectory as it applies to green infrastructure and stormwater management. But just a little bit more about myself. It's like I do have a background in ecology, in complex systems modeling, and in urban planning. And I use all of these perspectives to do couple human natural systems modeling to inform planning and policy. And what I've been focused on, and it's, like can we use complex systems reasoning in planning and policy to inform decisions? And we typically see like these kind of like three stages of incorporating this notion of this framework of complexity in policymaking and planning. One is like, we acknowledge, we know the world is complex, but it kind of like remains a black box. And it's more like of a descriptive or general observation of our cities or our settlements or our systems, our human systems. And so it's kind of like seeing complexity from afar or from outside. In a second stage, we actually use the tools to understand complexity from the inside. And so we do engage in complex systems reasoning and modeling. We think in terms of agents and their interactions or different components of a system and how they can interact with each other and play out as a dynamic. And we can understand, then what would happen if certain things changed. But then there's a third stage, which is incorporating that analysis and acknowledgement into decision-making and really moving from the analysis to practice. And what does it mean in terms of what different decisions do we need to make? And this is where a lot of my work has been between stage 2 and stage 3, and that I'm going to share a little bit of both. And this started with, way back when I was doing my dissertation, and I was interacting with planners as I was developing this model that coupled groundwater dynamics with land use change, and trying to assess how land use decisions, specifically zoning, might have direct and indirect effects on groundwater drawdown in Southeast Michigan in this case. What I realized is that, and this still happens today, it's changing, but it's happening today, that there's these two different worlds where scientists are separate from the stakeholders and the policymakers, where all of the deliberation about what we want about the future, where we're going to go as a society, as a community, happens separate from the modeling. And so what comes out of those deliberations are these requests for analysis to project, okay, given where we want to go, how do we get there? Or like how, what if we make certain decisions, what would happen? And so this puts a demand on scientists to come up with accurate models that can provide these best estimates, accurate as possible, to then feed back into the discussion that is happening with in the policy world. Now, what happens here is that because there's so much focus on prediction and accuracy, these models tend to be kind of complicated. They are kind of like black boxes for the people who are not involved in the modeling themselves. And they are developed to fulfill goals that are established elsewhere in this deliberative context. So there is little flexibility and possibility of adaptation and innovation in terms of like, should we rethink our goals, which are discussed only here, but not in relation to the analysis? And so it becomes harder to understand why is it that maybe we need to shift our goals that drive the system, because we don't understand how those goals are perhaps at the root of the problems that we are anticipating, because we don't understand the inner workings of the system if we're not involved. I've been trying to propose, and not just by myself, but with other colleagues in participatory modeling, is to really think of this process as an integrated process of analysis and decision making, where around the modeling activity, we have all of policymakers, constituents, and scientists modeling together and deliberating together, where we're all stakeholders engaged in this co-generation of knowledge and co-organization of knowledge and values. And together we can explore then policies and adapt our visions, our goals, the means towards those goals in that collaborative process. But there are challenges to this. There's definitely, interdisciplinary dialogue there that is challenging when we're talking across sectors, not just disciplines, but also sectors, private, public, etc., academic, non-academic. Spatial thinking and computer modeling can also be a challenge to a lot of people, even with all the technology that we are surrounded with nowadays. Confirmatory bias tends to be a major problem in these kinds of processes, especially when, this happens when we have models that provide outputs that align with our beliefs. And so we don't really inspect them because it already aligns. I trust them implicitly because they align with what I already believe in. But it could be a really flawed model, but I don't inspect it, versus a model that could be perfect, would be great, really useful, insightful, very rigorous in how it was built and validated and everything. But if it provides outputs that don't align with my beliefs, then I'm going to challenge it further. And then finally, in the policy and plan making world, we tend to focus a lot on consensus building, on reaching agreement. But the problem with that emphasis on consensus building and kind of like avoiding conflict is that we tend to then, in order to agree, we tend to generalize on recommendations to the point like, okay, we can agree that we want to be sustainable, but what does it mean on the ground? It just is, the recommendations are diluted to a point where, yeah, we agree, but it really is vague and it doesn't really give us direction on what to do on the ground. So for example, if we wanted to put green infrastructure, where would it put it? Where would we put it? What kind? And what amount? Who pays for it? What are some negative costs, or impacts of it? And who bears them? And so all of these kinds of questions are kind of diluted in that search for consensus. So this has led me to this part of my work, which is about, participatory modeling itself, and how can we use complex systems modeling in a collaborative setting to help us learn as a collective about the complexity that we face and that we're part of. And then not just that, but how does that learning that we do together lead to better planning, deliberation, and decision-making? So these are my guiding questions, but the context in which this is happening is in the context of green infrastructure planning for urban stormwater management. And this started a long time ago with some funding from the Illinois Environmental Protection Agency, because they were interested, the IEPA in Illinois was interested in starting to use green infrastructure more formally as a method of stormwater management and actually included in regulations and such. So I advised, like, if you want to do that, let's first try to generalize, because if you're going to be doing policy with it, let's try to see what general principles might exist there in terms of how to design green infrastructure in urban neighborhoods to be effective in stormwater management. So thinking of how much green infrastructure would a neighborhood need and where should it be placed in order for it to be effective for stormwater management. And there's, what I'm going to present now is part of a publication that I'm happy to share if people are interested. But essentially, we developed this process-based green infrastructure design model, LGRID, that is developed in NetLogo. It's actually accessible for free. I can also share the link to it where you can download if you're interested. But there are many flooding models out there. You might ask, like, why another one? Well, because most of the models that exist are either at the site level, but don't look necessarily at the context around the site, or they're very complicated and very detailed and sophisticated models that are at the watershed level, but take a lot of data and are just difficult to implement and run for a wide range of scenarios, which is what we would want to do in order to generalize to inform policy. And so in this particular model, we represent landscape explicitly. And what you see here is just like two Chicago blocks surrounded by streets, which are shown here with the yellow dots. And then in this block, you have impervious cover in gray, you've got soil or lawn cover in brown, and you've got like these, little squares here that are like bioswales or vegetated gardens representing the green infrastructure. There are sewer outlets spaced out as they would be in a block in Chicago, and this is, the general slope of the landscape that you can provide, and there are outlets also in the lower areas of this landscape. And so that's kind of like the basic landscape that we represented. And then we represented all the hydrological processes that go into different kinds of storms. So there's rain, the rain will fall in different kinds of land covers. Then depending on that land cover, there will be infiltration at different rates, depending on, again, what the cover is. Some of the water is drawn out by sewers. Some of it, there's evaporation and evapotranspiration, but in some of the soil and the green infrastructure. But during a storm, that's typically quite small. It's not very impactful during a storm. And then there's surface flow, essentially just like how water flows through the landscape as it tries to find equilibrium, right? And then outflow through the lowest part of the landscape. And so those are the basic processes and the order of events that happen in a simulation. And so to try to address the question of how much green infrastructure might be necessary in order to have an impact on stormwater management, we're thinking of just laying random bioswales, vegetated gardens in a landscape, in a fairly small landscape. I think that we tested initially 4 square kilometers. And assuming that 50% of this is impervious because it's an urban neighborhood, then what we see here is that as we increase green infrastructure in smaller storms, then, green infrastructure, if we have about, 10% already, the infiltration takes over and does more of the work than the sewer system would, and then there would be the runoff would be eliminated. The runoff going downstream to another neighborhood would be eliminated already at 10%. And here what we see is that the flooding on roads, which tends to happen more than on blocks, is also eliminated at 10% of green infrastructure for small storms. If we have larger storms, however, it would take much more. It would take about 30% of the coverage to be green infrastructure in order for there to be like no more runoff going downstream, no more flooding in the area, and for the storm water to be mainly captured by the green infrastructure and not tax the sewer system. To answer the question about how the spatial placement matters, we try different kinds of spatial layouts with the same amount of infrastructure. So the random is the same as I was showing you here, like in terms of like just randomly allocate bioswales. But then we try different kinds of designs. So for example, just curb cuts, which is the adjacent to roads. Then no curb cuts at all. It's random placement, but away from the roads. Then clustering green infrastructure upstream or clustering it downstream, thinking of, should we kind of like build bigger sponges in a neighborhood, so to speak, to absorb the water? Should we absorb the water where it lands first or where it pools later? So that's the upstream, downstream. And then a hybrid that essentially says, okay, let's pool it where let's group the green infrastructure where the water tends to pool in the lower areas, but then kind of follow the curves midstream and then upstream, just random locations. So we just tried the performance of these different kinds of spatial layouts. And so what we see here is that for small storms, again, we're seeing that, of course, as we add more green infrastructure, there's going to be, what you want to see here is that there's more infiltration and less going out through sewers and outflow. So we see these groupings here. And so in general, of course, as we, like before, we have more green infrastructure, it will do better. But we are starting to see here some patterns that really are notoriously bad. And those are the upstream and downstream. So when we cluster the infrastructure in larger bunches, that actually doesn't perform as well as if we spread it out. And for those that are spread out, it is the ones that are adjacent to roads that tend to perform better. So the mix, the one here, the one in red and the one in orange, which has a mix of both, random will also do quite well because some of them also will be curb cuts. But if we don't include curb cuts, they're not as good. And so that's what we're starting to observe here in terms of spatial layouts. With larger storms, it will take much more green infrastructure for the pattern to make a difference. At low coverages, well, there's so much water that it doesn't matter what pattern you're using, you're going to be just flooded. But when you get to 25% or 30%, you start to see again like different layouts performing differently. And again, what we're seeing is like some benefits of the curb cuts relative to, and the random placement relative to the clustering of green infrastructure. So what we can do with this is that we can start extracting some design principles. So on one hand, seeing that there are thresholds above which or below which green infrastructure can or cannot be, very effective depending on the kind of storm that you have. What this will look like will depend on each neighborhood, but there's some idea though that depending on the combination of land covers, there's going to be more or less effectiveness that needs to be studied for each neighborhood. And this idea that then the dispersed layouts do better than the clustered ones, and especially the advantage of the curb cuts. And the reason why they're advantageous is because they, on one hand, well, roads are really designed to channel water away from blocks and houses and property and into the sewer system. So curb cuts would enhance the job of the roads by keeping the water in the roads, directing it towards the road and keeping it there, but also slowing it down so that it doesn't, peak and overwhelm the sewer system. The other advantage of curb cuts that is not modeled, but it's, something to be discussed, is that they tend to be more in that public property. And so that facilitates things in terms of maintenance, because again, green infrastructure is very sensitive to maintenance. If you don't maintain it well, it won't work well. Having access to it because it's installed in public property enhances that maintenance or just facilitates it. And then we see some slight advantage of the hybrid layout also in larger storms. So the idea here is that if you don't have the ability to do a hybrid layout from the start, you could still start with focusing on curb cuts and then build a hybrid layout from it as time, resources, etc. allow. But if you can't do any of that, random is good. So it's definitely better than clustering. But what this model can do is that it can help at least start the conversation and start the the testing and of different kinds of designs to see what might work in particular neighborhoods. But I want to illustrate and go further, like why we need to think also of participatory modeling for this. And the reason is that, and I'll illustrate here with an example. So here there are two different scenarios. Here I don't just have bioswales, like here these are the bioswales, and here the light green represents the soil, the dark green represents buildings, and the dark gray represents building, and the light gray represents streets and alleys. And so what we have here is like we have scattered bioswales on the right, and on the left we have instead rain barrels all over the place. Because again, probably for you hydrologists, or for most of you, bioswales are rain barrels are not as necessarily impactful. But for a lot of people and for a lot of communities, they really think that rain barrels can help. And so we tried it. And here we're trying two different scenarios then, where we have rain barrels everywhere versus a few bioswales scattered. And what we're seeing here is that this area to the right, because this emulates, this is based on Blue Island, a neighborhood in the south side of Chicago. And this tends to be like sloped in that direction. And so that's why this area tends to be more flooded. What you see in pink are essentially the buildings that are being flooded, and you see a little bit shaded here. That's where the water pooled up, and so that's what that is indicating. And so if we compare the baseline without any green infrastructure with these two scenarios that we have here, we see that the 20-year present value cost of installation for the baseline clearly is zero, because we're not putting any green infrastructure. But we have about $39,000 in damages per storm. So all of these basements that are being flooded, that's what it amounts to. And 62% of the rain just flows downstream through here, through this outflow here. If we have rain barrels, we spend $14,000. The damages are reduced per storm by just a little bit, and we don't really make a dent on the outflow that goes downstream. When we have bioswales, they're much, much more expensive, over 20 years of maintenance, but they do reduce the damages per storm more significantly, and they also reduce the runoff downstream. So they're also reducing the damage downstream. So the question that I always ask here is like, well, which scenario is better? And so, well, if I'm a hydrologist, you probably, if you're like me, you probably say, well, the bioswales, because you have much more infiltration, you reduce the outflow going downstream by a lot more, you reduce the property damage by a lot more. But what if I'm a public official and I only have, I don't know, $15,000 to spend, and I don't really have more? Maybe at least I want to show my constituents that I'm doing something about this. At least I'm educating people. What if I'm the person living over here, and no matter what scenario I'm in, I'm still flooded and might as well not spend any money, because what for? I'm putting, investment into these scenarios, but they don't benefit me. So this is to say that simulations alone are not enough to give us answers of what needs to be done. Why? Because there are trade-offs. There are trade-offs across different variables. There are different costs, different benefits. There are different people who bear them. There are also utilities, and that might constrain what we can do. We cannot dig a bioswale everywhere. There might be, just electrical infrastructure or whatever, or gas pipelines underneath. And there are different values also, what different people prefer and what they perceive that the infrastructure will do for them. So we all want to do the right thing, but we might have very different ideas of what that is. And we can let computers, crunch data, but the solution space in relation also to our preferences, our collective preferences, is huge. By the time we're done computing, conditions and values might have changed. So, and people, because of confirmatory bias, for example, might not trust the output of that, all the computer crunching. So there's a lot of friction in that process. We need to build support for compromise to happen. So what that involves is not only just understanding how the biophysical world works, but it's also about understanding where we stand with our preferences, where other people stand with their preferences and needs, how we see the problem differently, how we see solutions differently, and then be able to evaluate these solutions as well, allowing in the context of a playful exploration that can be supportive of creativity and innovation. So again, it's not just about, simulating things. So what we did with my team is we developed this approach that is centered on the simulation, but has these other elements to it. And so we provide stakeholders or participants in a workshop that come together to work together, a tablet that has an app that allows them to then sort the variables of interest according to their preferences. For example, as a hydrologist, I would probably prioritize groundwater infiltration. So I would drag this up here. But if I'm a public official, maybe I would prioritize maybe investment or like to minimize the investment or minimize damage. Or if I'm a person living there, I would prioritize other things. So it allows for people to just state what their preferences are. And those preferences then are used as weights to evaluate the different scenarios. And we'll get to that in a minute. We also developed as part of this prototype, a way to, on a map that people are familiar with, and it's a map of their neighborhood, there are different tokens that represent different green infrastructure. And collectively, we can design green infrastructure scenarios for that particular neighborhood according to their flooding problems. And we've got this app that then will take a picture of that and convert it into an input that then goes into the simulation. The simulation runs in a couple of minutes. It produces outputs, and then those outputs are essentially downloaded onto the iPad that each participant has, but they're sorted and organized according to their preferences. So for example, here, each row is one of the scenarios tried. And the first one is all rain barrels everywhere. This one has green roofs in this corner of the neighborhood. This one has bioswales scattered regularly across the landscape. But then what I see here is just the raw data, again, sorted according to what I look at and what I think is most important. But then that sorting weighs each one of these factors differently. And so it gives me like this composite as a bar. And so this is probably the layout for a hydrologist, because they really like the one with the bioswales. Why? Because there's a lot more infiltration. It reduces the ponding and the accumulation of water on the streets and on the blocks versus the rain barrels, which don't do much of that at all. But then the other aspect of this app is that it lets us compare how I evaluate each scenario versus how other people evaluate the same scenarios. So here we have only two players. We have what we call the pedestrian and the policymaker, pedestrian being the resident. And as you can see, the resident doesn't like the rain barrels at all because they're still being very much affected by the flooding. The politician, on the other hand, or the public official really likes this. Why? Because it's inexpensive. It's a good investment in the sense that I don't need to spend a lot of public money on this. So I really like this approach, but from another perspective, it might not be as good. So what this visualization allows us to do is say, like, what, these two, and for example, roof gardens are very, very expensive. That's why the public official would not like it, but it might, even if it might have a little bit more of an impact. But what this visualization allows us to do is to say, collectively, as we discuss these together, we can say, well, you know what? These two don't seem to be very good. They might be good for me, but not for you, definitely. And overall, they're just not good. Why don't we focus on these ones, which tend to give us collectively a more benefit? And of these, which ones should we focus on? Should we focus on this one, which, seems to give you, the resident, a lot of benefit? Maybe not as much from my standpoint, but or should we focus on this one that is more equal in terms of like the benefit that it provides both? Do we go for this equality, even if it's overall, maybe the benefit is not as good, or we go for this one and we can start talking about maybe compensation. Maybe the residents can pay a little bit more in taxes to invest in this particular scenario if it's good overall, better for all of us. So that deliberation in relation to the simulation and in relation to our visualization through the diverse preferences then feeds back into either the design of the green infrastructure at the neighborhood level, because now I have a better understanding of how water flows through a system. I see it through the simulation, but I can also see what matters to you and what matters to me. And so trying to look for the benefits for both of us. But I can also understand now where you're coming from if you have different preferences, and maybe I resort my preferences because now I have a different view about the world. So we've tried this with different communities, and what we've seen is that there's definitely evidence of learning, innovation, and compromise. So assumptions and trade-offs become more transparent. We also structure the activity in very specific ways to allow participants to engage in systematic exploration and understand how do you conduct a systematic exploration with these kinds of tools. We see evidence of using gesturing and then mental modeling, not even needing the simulation anymore to anticipate how changing scenarios and changing characteristics of scenarios will lead to different performance. And so they can already do that mentally once they understand how the biophysical world works. And then also getting to the understanding that maybe green infrastructure cannot locally solve the problem, that we do need coordination, and that there needs to be other kinds of discussions. And it facilitated that broader, bigger picture of the problem and discussion of that problem. So what are some of the main takeaways about this? Is that this is very much a collaborative design enterprise. And in here, it's not that we produce models or tools for stakeholders, we produce them with them. All of this that I've shown you, we have developed with the stakeholders over time. And it does take time. It's about relationship building. The structured facilitation that I briefly mentioned was really key. So it's not just about the simulations and the tools that we developed and the apps, but it's really also how do we facilitate their use and structure the activities around the use of these tools with facilitators that can really enhance and systematize the exploration. And so we are definitely working on that aspect on how to support that facilitation process, because it is really key, and how to provide new interfaces for that. That's part of our current research. Then again, going back to this idea of consensus versus compromise. And so what we are seeing here is that by allowing people to see differences rather than try to push them back and avoid conflict, we are actually giving opportunity to the community to visualize these differences, visualize the different perspectives. And on one hand, understand what is it that we are giving up and what do we do about it? But on the other hand, it also supports further innovation. So it's really not about finding the best or the optimal solution to a problem, but what is a good enough solution that we can all live with, okay? And that we, again, knowing what we give up, what do we do about it, in a way that also allows for creative engagement with the problem and solution building before we can come up with like, okay, decisions, or that can support the decisions, or like, what is it that we're gonna do to solve this problem. And we see this as a scaffolded process. It's a point of entry. It's a point of entry to this particular problem, but it can also be a point of entry to more sophisticated tools that also analyze this problem, like more sophisticated models as well, that can give us more detail and more accuracy where it is needed. It can also be a point of entry to understand that people have different preferences and perspectives and views. And it can also finally be a point of entry for other complex problems that may be like this one, complex like this one, but we are already engaging in complex systems reasoning that can be transferred to other kinds of complex problems. And so again, a part of this is published. I'm happy to share a part of this work as well. We're very proud of this work. We actually won the inaugural American Planning Association Academic Tech Innovator Award in 2017. This is us at the conference. This is my technician, Dean Massey, co-authoring a lot of my work, and Leila Lyons, also, who is a learning scientist and computer scientist who helped in the development of some of these sets, and that's me. And so finally, just to end and give some time for question, Why do we do this? It's very onerous. It takes time, it takes resources. But why do I believe it's important? Because we have habits of thought and practice that prevent us from seeing new possibilities. And through the visualization of processes, biophysical processes, but also visualization of preferences and how we filter outcomes through our values and through our diverse values, then we collectively are empowered to see differences and address them rather than push them back and avoid them. And so the models, the interface, the facilitation structures that we develop can support or should be designed to support the exploration and evolution of not just understanding, but also our valuation of that understanding. Because innovation is in the relationship with each other and with the tools as prosthetic devices for decision making. They cannot supplant human judgment. We cannot get rid of human judgments. Humans have to be part of the decision-making process, but we can provide technical enhancements, but not fixes. We cannot have technical fixes without social learning. And so that is what we need to support with these kinds of approaches. This has huge consequences for our ability to support innovation, coming up with novel solutions, but also for democracy. And especially nowadays where there's so much going on in terms of misinformation, disinformation, polarization, this kind of approach can strengthen the democratic process of decision-making in a context of working with difference rather than trying to eliminate it, and also working with complexity and understanding it instead of trying to assume it away or simplifying it to the point of really not being able to handle it effectively because we've simplified it away. Or we've packaged it into a black box that we don't quite understand. So the planning tools and the social protocols around their use should support this kind of work. And this is really where innovation happens. And this is, again, critical for democracy, for innovation, and that then feeds to our ability to be resilient and sustainable as communities. So as I mentioned, I didn't work alone. I worked with a lot of people and funding sources that have supported this work over the years. I'm happy to share more. This is my email if you want to reach out, but thank you for the opportunity, and I welcome any questions that might have come up.
Thank you for that presentation, Moira. That was really great. I have a few questions prepared, but it looks like we're actually getting a lot from the audience. I'm going to dive into those first.
I'm going to stop sharing. Is that okay? Is that what I should do?
Sure. Yeah, we can always share your email address with anybody after as well. Okay. So first, there's a few technical questions, more details people wanted about your model. So first question is, what is considered by a small storm and a large storm in the context of the model you showed?
Yeah. So let me think. I think there was a 100-year or 5-year storm but again, these definitions have changed. This was done back 10 years ago. So some of these definitions have changed, but essentially it was assuming that, there would be smaller storms that would occur, with a frequency of every 5 years versus the huge ones, which were every 100 years. And what we did is we just took the different amount of precipitation and just created a hydrograph for it. Kind of like a very stylized hydrograph. So it's not based on the time series of a precipitation event. We just created it from just general values for these storms of the total amount of precipitation and the amount of time. So it could have been a 24-hour storm or a shorter storm, etc.
Okay. Awesome. The next one is, how do you calculate the size and placement of each green infrastructure tool you feel is optimal to reducing future flooding and flood risk?
Okay, say that again.
How do you calculate the size and placement of each green infrastructure tool you feel is optimal to reducing future flooding and flood risk?
Okay, so what you're asking, so again, we're talking about optimality when, because of the things that I said, I'm not sure that we can talk about optimality, okay? But if we wanted to design green infrastructure placement, essentially what we're doing here is each parcel of land or each block is divided into different cells. Each cell has a particular dimension, and we are calculating essentially the size of the infrastructure based on that cell, but that can be changed. So you can try different things depending on the context that you're testing. So the model is very flexible to allow you to try different dimensions and specifications for the grid infrastructure.
The next one is related is, could you please mention the model you're using to calculate the volume reduction percentage using green infrastructure?
So essentially, this is a process-based model, and it's again, like, I'm happy to give you the link where you can download it and inspect it yourself. But essentially, it builds on other kinds of models as well, in terms of like how much of the water that falls on a cell will infiltrate, how much will flow to other cells, et cetera, depending on the hydraulic gradient between cells. And so that's essentially, it's just really building on basic hydrological mechanisms to see how much goes into a cell through precipitation, how much goes out through infiltration and sewers, and then how much flows among cells based on the differences in the hydraulic head. That's just kind of like the essential processes that go on in this process-based model. And so it's going to be different depending on the land cover, the slope, the kind of storm it is. So again, it's just calculated through that process, but the equations or the mechanisms are, essentially the same. And I can share, by just giving you access to the LGrid model that's posted on the web.
That commenter would love if you could share the link. So either if that's something that you can share with the host, or if you have that available to put in the chat.
Yes, I'll put it in the chat in a second. Yeah, but if you want to keep asking questions.
Yes. So there are a few, and just let me know if you feel your answers have already covered this, but a few of the questions are really questions are about how you're converting your social viewer data into numerical modeling.
So right, that is a huge task in itself. So one is like how do you attach a weight to the preferences? That's kind of arbitrary, and it's shown in the pie chart. If you remember the visualization, but then it's how we transform these outputs into scores that then need to be normalized in order to come up with this composite score. That's what the question is about, correct? Like a composite score?
Believe so.
Yeah.
If somebody has more information on that, they can post it in the chat.
Yes. So that is something that required a lot of deliberation, and it's also something that we ran by our stakeholders to make sure that whatever we came up with made sense to them. Okay, and so that's something that I can give you the details, not right now because I would have to dig it out and share it with you, because I don't have it right in front of me, but it's something that, again, I would strongly encourage that if you're working on metrics like that you work on them and figure them out with your stakeholders to make sure that it's transparent and it's something that it's meaningful to them. And it's not just some mathematical thing that we did behind the scenes and nobody understands what it really means.
So on a related question, one of the attendees would like to know, how can someone interested learn more about this engagement process to implement it in other topics?
So that's part of the literature that we're trying to, get out there. There are some articles that, again, I'm happy to share that try to look at participatory modeling in general and with different approaches at how do we engage with it, what are some of the lessons that we learned, what are the things that we should do, what are things that we should not do. So I'm happy to share some literature on that, but there's a lot more to be done. This is a fairly new area of work, and it's so diverse in its application that it is hard to come up with generalizations. And for the kinds of things that this particular audience might be interested in, there are definitely more detailed approaches that need to be refined and developed and refined for these particular applications. So again, I'm happy to share the literature that I've been part of, and if you find that useful, and happy to engage with further conversations, especially as we think of like, what is needed? What else do we need to do here? Which I know is a lot, but like, what are some avenues that we could explore together as a community?
So that's actually a good leeway. So one of the questions that I had prepared is, do you have opportunities to collaborate or other opportunities in general you'd like to share with the audience today? Are there ways that they could connect with you or each other moving forward?
So I think that some public agencies are definitely increasingly interested in working in participatory modeling or engaged research. And of course, there are other kinds of donors, sponsors, et cetera, that are mission driven and that really care about working with stakeholders. So there are growing opportunities that are asking for this kind of work that I would be more than happy. If you're interested, please reach out to me. I'd be more than happy to work with you to try to continue developing these applications. So the applications as tools and approaches, but also the application on particular cases, because it's necessary. We need to do this. This is absolutely necessary and urgent. And so if you're interested, just let me know, and I'm happy to work with you and to try to figure out and explore possibilities for collaboration together.
Awesome. And if anybody has trouble reaching Moira, feel free to reach out to us CUAHSI staff, and we'd be happy to put you in touch as well.
Please.
So another question is, in your social viewer approach, why worry about the policymaker preferences? Policy shouldn't be designed to make policymakers happy. It should maximize the benefits for the community. So I guess, could you talk about how you're balancing community versus policy needs and how you make those decisions?
That's a great comment. Where do I put, I want to share the, hold on, let me put in the chat here, I'm putting the, oh, that's the video. Sorry, that's not what I wanted to share with you all. Sorry.
As long as you drop it down to share with everybody, not just the host and panelists, then the audience can see as well.
Yeah, hold on. Here we go. This is what I wanted to share with everybody. That's just a video that shows a little bit of what I already presented. Sorry, did you say not to put it on the chat or yes?
Yeah, just there's a little button you can drop down and just make sure it says to share to everybody.
Everyone, there you go. So this is where you can download the model that I just shared with you. Okay. So it's a great question. But if there are policymakers in the audience, it probably might be a little bit hurt, you know, by what by that question. Because first of all, policymakers are supposed to represent their constituents. And so they do represent some of the preferences, needs, and concerns of the people that we are hopefully serving. They are also constituents themselves. They're also stakeholders themselves. They absolutely have to be part of the picture, because maybe a resident doesn't have a full idea of the tax base, the resources available, and all the different needs and wants of a community in its diversity. But a policymaker would. They would have a better idea because they are managing budgets. They are managing different and very diverse sets of expectations. So they absolutely must be part of this conversation. I hope that answers your question.
All right. Our next question is, could you talk a little about strategies to come to consensus or bringing reluctant participants into decision-making and change?
Well, one thing that I learned is that if participants are reluctant, don't push them because it backfires. And so you can only go as far as you've got to meet the stakeholders where they are. And that's something that we're not necessarily taught as scientists, right? But it's something that I think it's increasingly important. And we've got to develop that sensitivity and that emotional IQ to address and deal and interact and build relationships with people that are not like us, that are different, that might have different views of the world, different perspective, different preferences. And so again, remember, it's not about coming to consensus, because consensus can lead to groupthink, which is not necessarily a good thing. Consensus can lead to vagueness, which is also not a good thing. We want to engage in productive conflict, if anything, or sometimes they call it productive or constructive friction or something like that. There are different terms for it. So that if there is conflict, if there is difference, if there is disparity, that we actually build something from it instead of just like pushing it away. And I think that if we can create an environment where people feel safe, in which they can express their views, their perspectives, their concerns and their needs, and they're somehow made visible and valid, and they have a space in the deliberation table, then everybody can contribute, and that can lead to innovation as necessary, and that can encourage people to stay engaged. At least that's what I've seen in my experience, that if you provide that platform, if you provide that support, then people actually want to engage, and they don't only want to engage, they want to stay engaged, and they want to bring others along. So that is what is important. It's really about focusing on the relationship building as a genuine relationship building process.
Yeah, I think that's really important in this kind of research for sure. So another question is, have you considered what happens when the model used or that's developed in the public participation process produces a different result that might conflict with what would be perceived as a more accurate or different kind of model or design? Does this have any impact on public support?
It has definitely an impact. I can tell you that. And so that's why it's incredibly important to build these tools in collaboration with the diverse participants so that those aspects are ironed out ahead of time and over time, rather than, well, we built this separately, nobody has seen it, now I present it publicly and it completely conflicts with what people believe. That is not going to go very well. It's probably going to just generate a lot of anxiety, distrust, and it's just not going to be very helpful. What I find more helpful and what I'm advocating for is engaging in the model building process and the model testing process with key stakeholders that represent the scientists, that represent the hydrologists, that represent the residents, the policymakers, etc., so that we're all kind of like working on it together, and there are no unpleasant surprises that we don't know how to deal with in a very public and high stakes kind of event.
We have a few more about the technicals of your model. So have you considered other green infrastructure or low impact development strategies such as infiltration trenches, rain gardens, bioretention cells, and then sort of as a follow-up, if you use a mixed use of rain barrels and these other strategies, could you achieve a larger reduction in peak flow, and would it be effective for a 100-year storm event?
Yeah, so we actually tried different kinds of combinations. So that the kinds of green infrastructure that we simulated at the end, the ones that I showed you, like the simulations themselves, were just rain gardens, bioswales, where you have engineered soil and you have vegetation, and it's a very generic kind of, bioswale kind of thing. But in the ones that we use with stakeholders, we had a combination of rain barrels, roof gardens, permeable pavers, and the bioswales. And they did try different things. And sometimes it made sense to try a combination of things. The other thing to note here is that we were only looking at volume reduction, but there are co-benefits that come from the different types of green infrastructure that were not considered. But that's something that is in our to-do list of like just bringing in these other benefits, that as well as we are evaluating different scenarios for, different kinds of impacts that these different green infrastructure types might have. But what the model allows is to expand on that. So you can add in more specifications of these green infrastructures. You can add different types as well.
I think we have kind of an interesting question for potentially our last one. We'll make sure we keep to our 1 o'clock deadline, is how do you take into account fuzzy implementation? The regulations and provisions could be on the books, but regulators could intentionally or unintentionally be not enforcing the provisions. For example, planners usually copy regulations from their local neighbors, but if wrong practices are copied, this causes cascading effects. Also, some regulators misunderstand legal requirements such as an inadequate understanding of the structure of law and rely on past practices. Does your type of modeling take this into account at all?
Absolutely. I mean, in great part, we did this to avoid all of that. So just being able to actually show, when you do this in this way, this is what happens. It's not what you think is going to happen necessarily. It's when we actually simulate the biophysical process in space and time, what happens? Because a lot of this is, as you say, through copying, past practice, precedent. So copying has a negative connotation. Let's say precedent, which is very important in planning and policy and law. But without necessarily a foundation, a solid foundation on the science. So this is a way to really bring the science into the conversation so that that policy deliberation can be better informed with not just mental models that are not based on hydrology, or policy models that just are based on precedent, but not much more, or whatever they're doing in somewhere else, or whomever told me. No, it's like, okay, this is based on what we know of how soils work, how water runs through the landscape, etc. So now we can test these out and say, like, okay, if we did this and that, this is the likely outcome, and that can inform then our policy and regulations. That was the intent of this whole approach.
Awesome. And I think that's a really great note to end on. So I guess with 1 minute left, is there anything you'd like to wrap up or conclude on?
No, thank you very much again for the opportunity. Please, if in the audience, if you're interested, continuing the conversations beyond this presentation, please do not hesitate. I always love to explore different ideas, possibilities, opportunities for collaboration. So please feel free to reach out to me.
Awesome. Thank you so much.
Thank you. Thank you for inviting me.